Okay, so let us now move on to question 78. So, a surfer is catching a wave. She starts at the top of the wave with a speed of 1.4 meters per second and then moves down the wave until her speed increases to 9.5 meters per second. So the drop in her vertical height is 2.7 meters. So if her mass is 59 kilos, how much work is done by the force of the wave? Okay, so a couple of things here that we need to be aware of. So the first one is, she has an initial velocity of 1.4 meters per second. Her final velocity is 9.5 meters per second. She has a total displacement of 2.7 meters. Her mass is 59 kilos. And the question is asking for the amount of work that is done. Okay, so big thing that we need to do here is we need to be aware that work is the change in energy resulting in movement, and that kinetic energy and potential energy are related in that, kinetic energy and potential energy will equal to the total amount of energy in that system. So, what we do is, because our surfer here is starting at a specific speed and finishing at a specific speed, we can't just assume that gravitational potential energy and the kinetic energy are going to be zero. So what we do is, we know that the work done by the wave is going to be the difference in the kinetic energy, so that's going to be 1/2 mv squared final minus 1/2 mv squared initial plus the difference in the gravitational potential energy. So that's going to be mgh final minus mgh initial. Now the reason why is that, remember that the law of conservation of energy states that energy cannot be created nor destroyed. So what's going on here is we are seeing the change in the kinetic energy and the change in gravitational energy, and the result of these two is going to be the work done by the wave, because that has led to the change in both the kinetic and the gravitational potential energy. So the big thing here again that I'm seeing is we've got 1/2 of the mass times velocity and 1/2 of the mass times velocity. So we can simplify this to be 1/2 of the mass v squared final minus v squared initial, because her mass here is not changing, and essentially we're just timesing the velocity by the same values here. So we can simplify it to this. Now we add it, now it's the same deal here, mass and gravity. Her mass isn't changing, neither is gravity, so we can go mg bracket height final minus height initial, like so. Now we start to add in our values. So we go, work is equal to 1/2 of the mass, which is going to be 59 kilos, bracket, final velocity minus initial velocity, so 9.5 and 1.4, plus her mass and gravity, so we're going to have 59 kilos, times 9.8 meters per second squared. And then we're going to multiply that by the difference in height. So it's going to be her final height was, so the drop in her vertical height is 2.7 meters. So we don't know how high she started. All we know is that she fell 2.7 meters. So I'm going to put negative 2.7 meters, because that's how far she fell downwards. Okay, so I'm indicating that negative means that she's going down. So we start to simplify here. So we've got 1.4 squared and 9.5 squared, and we subtract them. And then we've got 1/2 of 59, so we solve this chunk here. So that's going to equal to 2,604.56 plus we're going to have 59 kilos, 9.8 meters per second squared, and multiply that by negative 2.7, and that's going to give us negative 1,513.35, which means that we've got 2,604 minus 1,513, which means that the total work done by the wave is going to equal to 1,091 joules, and that is our final answer. Okay guys, so we're now going to move on to question 45. So again, just be aware that this is a part of the challenge questions, so these ones will be a little bit more tricky than the ones that we've been dealing with earlier. So, two pole vaulters just clear the bar at the same height. So the first lands at a speed of 8.9 meters per second, and the second pole vaulter lands at a speed of 9 meters per second. Okay, so the first vaulter clears the bar at a speed of 1 meter per second. So at the top of the hurdle, when they're leaping over, they're clearing it at 1 meters per second. Ignoring air resistance, what is the speed that the second vaulter will clear the bar? Okay, so essentially they want to know what is the speed of the second pole vaulter as they clear the particular bar at a certain height, which we don't know what it is. We just know it's the same height. So the biggest thing that I'm seeing here is we are comparing two pole vaulters, but we know that they're jumping at the same height. So I'm going to try and use that to our advantage. So what we're going to do is, because we have most information about pole vaulter number 1, I'm going to try and use the information for vaulter number 1 to try and find out how high this bar is. So, we know that with vaulter number 1, so the first thing I'm going to do is I'm going to use the law of conservation of energy. So with vaulter number 1, I'm going to compare the kinetic and potential energy from the bottom, so when the pole vaulter hits the ground, and when they're at the peak, so when their gravitational potential energy is at its highest. So I can do this by going. So what I've done is I've got our kinetic and potential energy, but I've just compared them, so we've got the kinetic and potential energy when the vaulter is in the air, and we've got the kinetic and potential energy when the vaulter is on the ground. Now, the key thing here is when they land, so they're actually hitting the ground, their gravitational potential energy is going to be 0, okay, because they've got nowhere else to fall. So we can eliminate this one because there is no energy left in there. Another thing we can do here too is that the mass of vaulter number 1 is used in all of the kinetic and potential energy equations here, and the masses are not changing, so we can eliminate mass from the equation. So that's going to leave us with 1/2 of the velocity squared plus gh equals 1/2 velocity on the ground. So we can start to add some values in now. So we have 1/2 times the velocity in the air, which is 1 meter, plus gravity times height. So I've got gravity, which is going to be 9.8 meters per second squared, multiplied by the height, which we don't know, is going to equal to 1/2 of the velocity on the ground. So the first vaulter lands at a speed of 8.9 meters per second. So we've got 1/2 of 8.9 meters per second squared. Okay, so that means that we're going to have 1/2 of 1, which is going to be 0.5, and 1 squared, so 1 times 1 is 1. So we're going to have 0.5 plus 9.8 meters per second squared times height. So we're going to have 9.8 h is equal to 1/2 of 8.9 meters per second squared. So if we're going to have 8.9 squared, so 8.9 squared divided by 2, or half, is going to give us 39.61. So what we can do now is we can do some rearranging here. So we have 0.5, this is an addition, so it's going to turn into a subtraction. And 9.8 and h, we have a multiply, so that's going to turn into a divide. So we're going to have h is equal to 39.61 minus 0.5, pop those in brackets, divided by 9.8, which means that we're going to have a height of 3.99 meters. Okay, so this is really useful because now we can use this height to help solve for volt number 2, or volta number 2. So again, we use the same mechanism that we did here. Now again, when the volta is landing on the floor, that means that they're going to have no gravitational potential energy, so we can eliminate this one. And we also know that the mass of the volta is not going to change. So again, we have 1/2 of the velocity in the air, which we don't know, that's what we're wanting to calculate, plus the gravity times height, so we've got 9.8 times the height, which is 3.99, is equal to 1/2 of the velocity on the ground. So the second landed at a speed at 9 meters per second, squared. Okay, so again, now we need to rearrange everything so that we have everything by itself. We'll pop these in brackets here. So we're going to have 1/2 VA squared plus, so 9.8 multiplied by 3.99, which is going to give us 39.1. It's going to equal to 9 squared divided by 2. So 9 9s are 81 divided by 2, so that's going to give us 40.5. Alrighty, so we've got an addition here, so I'm going to take this and rearrange it. So we've got 1/2 VA squared is equal to 40.5 minus 39.1. And we've got 1/2 here, so I move this 2 over, so the operation between the 2 and the 1 is a divide. So I move that over, it's going to turn it into a times. So that's going to turn this 1/2 into a multiply. Which means we've got v squared is equal to 2.8 meters per second. Now again, this is squared. So in order to get rid of this squared, we have to square root this. So the square root of 2.8 is going to give us a final velocity of 1.67 meters per second. So this means that the second volta cleared the pole, which was at a height of 3.99 meters, with a velocity of 1.67 meters per second. Okay, now let us have a look at question 83, part A. So, a basketball which has a mass of 600 grams is dropped from rest from a height of 1.05 meters. Okay. It then rebounds to a height of 0.57 meters. So we want to know how much mechanical energy was lost during the collision with the floor. Okay, so the big thing here is we need to find out two things because it wants to know how much mechanical energy was lost when it bounced on the floor because it's gone from a height of 1.05 meters. So if we dropped that ball and it bounced on the floor and it bounced back up with perfect elastic collision where absolutely no energy was lost, it would rebound to a total height of 1.05 meters. But it's not. It's only bouncing back up to 0.57 meters. So what we need to do is we need to calculate, okay, what is the total energy from dropping the ball from 1.05 meters to the ground? Then we need to calculate how much energy would it take for the ball to go from the ground to 0.57 meters, and then we can subtract the difference between them because that's going to tell us how much energy was lost. So Part A, what we need to do is we need to look at the total mechanical energy. So remembering that the total energy is the kinetic energy plus the potential energy. So remembering we are going to use the formula. So now we need to do a quick check, make sure that we have all of these values. So we have the mass, we know gravity, that's fine, we know the height, but we don't know the velocity. But here's the thing, we can calculate the velocity. So we know that we have, it's from rest, we have a mass, and we have a distance. So we can go v squared is equal to VO squared plus 2AX. So again, we're solving for velocity here, for v squared, because we need v squared. So v squared is equal to VO squared. Now, the initial velocity, it says from rest, so this is 0, plus 2 times the acceleration, which is going to be gravity, 9.8 meters per second squared, times the displacement, which is 1.05 meters. So it means that the total velocity squared is 2 times 9.8 times 1.05, which is going to give us 20.58 meters per second. Now there's no need to take the square root to find just velocity, because in this formula we want velocity squared, so that's okay. So we can now use this formula to find the total energy in dropping this basketball here. So we're going to have 1/2 of the mass, which is 0.6, times the velocity, which is going to be 20.58, plus the gravitational potential energy. So we're going to have 0.6 kilos times 9.8 meters per second squared, multiplied by the height, which is 1.05 meters. So we simplify this down, so 1/2 of 0.6 times 20.58, that's going to give us 6.174. And then we go 1.05 times 9.8 multiplied by 0.6 is going to give us 6.27. So it means these two combined is going to give us an energy total of 12.44 joules. Okay, so that's really interesting. So it means the total amount of mechanical energy from dropping a ball from a height of 1.05 meters, it's going to cost 12.44 joules. So what we need to do now is we need to calculate how much energy it would take for the basketball to bounce at a height of 0.57 meters. So again, we do the same sort of thing. So we go the energy is equal to 1/2 mv squared plus mgh. So we've got the energy is equal to 1/2 the mass, which is 0.6, times the velocity squared. So the velocity is going to be 20.58. Because that is the speed in which the ball is bouncing on the ground. So as it's hitting that ground and bouncing back up, we know that's the speed in which it's going to be traveling at. Plus the mass, which is 0.6 kilograms, times gravity, which is 9.8 meters per second squared, multiplied by the height, which is going to be 0.57. Okay, so it's the same deal. We just go through and we simplify. So we've got 1/2 0.6 times 20.58. So it's going to be 6.174 plus 0.6 times 9.8 times 0.57. So that's going to give us 3.35. So by adding these together, we're going to get a total of 9.52 joules. Now, to find the total mechanical energy that was lost, what we do is we need to go the total energy, which was 12.44 joules, minus the energy that it took to bounce the ball up to 0.57 meters, which was 9.52 joules, will equal total energy lost. So this means that the total energy lost is going to equal 2.9 joules. And that is our final answer. So we've got the same question here, but we need to have a look at part B. So part B said, a basketball player is dribbling a ball from a height of 1.05 meters by exerting a constant downward force on it for a distance of 0.08 meters. So in dribbling, the player compensates for the mechanical energy that was lost during each bounce. So if the ball returns to a height of 1.05 meters, what is the magnitude of the force? Okay, so this is very interesting. So it means that the total amount of energy that was lost is being replenished by the player in terms of him pushing the ball down. So this is work. So this is what he's doing. He is applying work to the ball in terms of a force, a downward force, by pressing the ball down so that it hits the ground with more energy, meaning that it will bounce up to its original height of 1.05 meters. So what we do is, we remember that the work is force times distance, or displacement I should say rather. Now we know the work because we know that the total amount of energy lost was 2.9 joules. So it means we can go 2.9 joules is equal to the force. We don't know what the force is because that is what the question is asking us. It's asking for the magnitude of the force times the distance. Now don't fall into the trap of using the 1.05 meters because he is exerting a downward force of 0.08 meters. So that is the distance in which he's pushing down on the ball. So that's going to be 0.08 meters. So we rearrange this. So this is a multiply. So this turns into a divide. So we've got 2.9 joules divided by 0.08 meters is equal to force. So that means that the total force is going to equal to 36.5 newtons. Okay guys, so that now finishes up Module 14 Video 2. So thank you very much for joining me today. I hope you all enjoyed it. If you do have any questions, queries, ideas, suggestions, please feel free to email me at b.grant@griffith.edu.au. Please don't forget to complete the survey down below. It really does help me out a lot. Best of luck with your studies and your upcoming exams, and I'll see you all next time.